This video is going to run through some techniques that we can use to solve both logarithmic and exponential equations. We'll start with exponential equations. That's equations where the variable, or the x, is part of the exponent. We'll discuss 3 different methods that can be used in this video. So let's just start with an example. I have the equation 9 times 3 to the 2x equals 81. The first method we're going to use involves writing everything, both sides, with the exact same base. This method only works in special cases where all the numbers can be written with the same base. And so what I mean by this is 9, 81, and then we have a 3. These are all powers of 3. 9 is 3 squared. And then we've got this times 3 to the 2x. And 81 is the same as 3 to the 4th. So notice I can rewrite everything with base 3. Then we can use our laws of exponents to simplify. When we multiply, we add the exponents. So 3 squared times 3 to the 2x is 3 to the 2 plus 2x. So now we've got 3 to the 2 plus 2x equals 3 to the 4th. And the idea here is exponential functions are 1 to 1. And that means if your outputs are the same, if these powers of 3 are going to be equal, the inputs have to be the same. So because we have a single power of 3 on each side, we can actually ignore the 3's. The only way this statement is true is if these exponents, 2 plus 2x and 4, are equal. So 2 plus 2x has to equal 4. That's something I can solve. I subtract the 2 from both sides. 2x equals 2. Divide by 2. X equals 1. Let's do a second example using the exact same method. Let's see if we can solve 1/2 to the x times 8 to the x plus 1 equals 4 to the 5th. All of these numbers can be written as powers of 2. 1/2 is the same as 2 to the negative 1. So I've got 2 to the negative 1 to the x. 8 is the same as 2 to the 3rd. So times 2 to the 3rd to the x plus 1. And 4 is 2 squared, equals 2 squared to the 5th. In all 3 of these situations, we can multiply the exponents. That's our power rule. And so this equation becomes 2 to the negative x times 2 to the 3x plus 3. Notice I multiplied the 3 by both the x and the plus 1. I had to distribute there. And then equals 2 to the 10th. That was 2 times 5 gave me the 10th. On the left-hand side, we have a product, so we can add the exponents. The left-hand side is going to turn to 2 to the, we can figure out what negative x plus 3x plus 3 is. We can combine the negative x plus 3x to a 2x. And so now we've got the equation 2 to the 2x plus 3 equals 2 to the 10th. Since we have condensed this down to the exact same base on both sides, that means these exponents have to be equal. In other words, 2x plus 3 has to equal 10. So I'm going to subtract 3 from both sides. 2x equals 7. Divide by 2. X equals 7/2. Now this technique is only going to work if you have nice numbers, numbers that can all be written with the exact same base. And that's not always going to be true. And so I'm going to show you a second method. In the second method, we are going to take the log of both sides to basically undo the exponential. So I have the equation 5 to the 3x plus 2 equals 1. The inverse of 5 to a power is log base 5. So to get rid of that exponential, I'm going to take log base 5 of both sides. That gives me log base 5 of 5 to the 3x plus 2 equals log base 5 of 1. On the left-hand side, this log base 5 of 5 to the 3x plus 2, these are inverse operations, and we're just going to be left with the 3x plus 2. You can kind of think of the log and the 5 kind of canceling each other out. I guess they're not really canceling, but they're inverse operations, so they're undoing each other, and we're just left with that 3x plus 2 equals log base 5 of 1. And log base 5 of 1 is something I can compute. 5 to what power equals 1? The answer is 0. 5 to the 0 is 1. So subtract the 2. 3x equals negative 2. Divide by 3. X is negative 2/3. Here's another example. 4 times e to the 5x equals 8. Now, before we take the log of both sides, we do want to isolate that exponential. We want the exponential term to be by itself, and then we can use the same method as before, where we'll take the log of both sides to try to get rid of that exponential expression. So the first thing I'm going to do here is divide both sides by 4, and that gives me e to the 5x equals 2. Now that I have my exponential by itself, left-hand side just has an exponential, I'm going to use the exact same method I used in the previous example. I'm going to take the log of both sides. This time we have base e, so I'm going to take log base e, or natural log of both sides. Natural log of e to the 5x is just 5x. Same reasoning as in the previous example. Log base e to a power are inverse operations. They undo each other, and we're just left with that 5x. So 5x equals ln 2, and then I can take natural log of 2, divide it by 5 to get x. So my solution to this equation is natural log 2 divided by 5. You can leave the answer like that, or if you want a decimal approximation, that's something you could put into your calculator. Natural log of 2, and then divided by 5. Here's another one. Let's use the same method. We have an exponential by itself, 3 to the x plus 2 equals 7. To get rid of the exponential, it's 3 to a power. I'm going to take log base 3 of both sides. Log base 3 of 3 to the x plus 2 equals log base 3 of 7. The left-hand side can be simplified down to x plus 2. Same reasoning as before, log base 3, 3 to a power. Those are inverse functions, just left with x plus 2 equals log base 3 of 7. To solve for x, we have to subtract the 2. So now I have log base 3 of 7 minus 2. If I wanted to get a decimal approximation and put this into a calculator, I will have to use that change of base formula. My calculator doesn't have a button for log base 3. So I'm going to change the base to e, because I have an ln button on my calculator. So log base 3 of 7 becomes ln 7 divided by ln 3. And this is now something that we can type into our calculator, and I got a decimal approximation of negative 0.2288, and I rounded a little bit there. Now, if you don't want to remember or use the change of base formula, let me show you another way that we can get the exact same answer without actually using this change of base formula. So another option we have is we could take log of both sides, but this time let's take a log that has a base that we can work with in our calculator. So let's see what happens if we take natural log of both sides. So now I've got natural log of 3 to the x plus 2 equals natural log of 7. We can't use that inverse property here to cancel things out, but we do have a property that says if you have log of an exponential, you can take that exponent, move it out front, and it becomes a product. And so now we have the quantity x plus 2 times ln 3 equals ln 7. One way to solve for x is we could divide both sides by ln 3. Now I've got x plus 2 equals natural log 7 divided by natural log 3, and then I can minus the 2. This is the exact same answer we got before. It's just that change of base formula was actually done for us at the beginning of the problem. So x is natural log 7 divided by natural log 3 minus 2. This is something we could put into a calculator if we want to get a decimal approximation. This method of taking natural log of both sides also works really well when you have an equation with two different bases. So for example, if I want to solve 2 to the x plus 3 equals 5 to the x. I have different bases, base 2 and base 5. And so I'm going to go ahead and just take natural log of both sides. I'm choosing natural log because I have a button in my calculator that says ln, but I could also choose log base 10. I also have a button in my calculator for log base 10. My next step is to use that property and take the exponents, move them out front, and write them as products. So now I have the quantity x plus 3 times ln 2 equals x times ln 5. I'm going to go ahead and get rid of the parentheses. I'm going to distribute that ln 2. So now I've got x times ln 2 plus 3 times ln 2 equals x times ln 5. I'm trying to solve for x, so I want all the x's on one side of the equation. To do that, I'm going to take this x ln 2 and I'm going to subtract it to move it to the right-hand side. So I subtract x ln 2 from both sides. That gives me 3 ln 2 equals x ln 5 minus x ln 2. I'm trying to solve for x, so I'm going to factor the x out of the right-hand side, and now it's x times ln 5 minus ln 2. Finally, to finish, we can divide both sides by ln 5 minus ln 2, and there's my final answer, 3 natural log of 2 divided by natural log of 5 minus natural log of 2. And that is something we can put into a calculator if we wanted to obtain a decimal approximation. All right, I have a third and final method I'm going to show you for exponential equations. And the third method is going to work for equations that are considered to be quadratic type, so only for special equations. I have the equation e to the 2x minus e to the x minus 6 equals 0. This kind of looks like a quadratic equation in the sense that there are 3 terms. And if we take a closer look, that e to the 2x is the same thing as e to the x squared. So we've got something squared minus the something minus 6. And so we could do a change of variables. Let's let u equal e to the x. Then this first term, e to the x squared, is going to turn into a u squared. So now I've got u squared minus u minus 6 equals 0. And I know how to solve quadratic equations. We can try to factor, and if we can't factor, we can always use the quadratic formula. This one, though, we can factor because 3 times 2 is 6, and if I make it a minus 3 and a plus 2, that'll definitely add up to negative 1. So my factors are u minus 3 and u plus 2. That tells me that u has to equal 3, or u could equal negative 2. We're not actually done, though, because u was e to the x. So now we've got 2 equations. E to the x could equal 3, or e to the x could equal negative 2. We can rewrite these in log form. E to the x equals 3 is equivalent to x equals ln 3. If that's not clear, you could also take natural log of both sides. Natural log of e to the x turns into an x, so x is ln 3. E to the x equals negative 2. If you take log of both sides, you get x equals natural log of negative 2. So it looks like we have two solutions, but we can't take the log of a negative number. It's not in the domain of that logarithm. So we actually only have one solution, x equals natural log of 3. Now let's move on to solving equations that involve logs. One method is to isolate the log, get the log by itself, and then put in exponential form. So I've got the equation 2 natural log x plus 3 equals 5. So I'm going to try to get this natural log x by itself. To do that, I minus 3 from both sides. That gives me 2 ln x equals 2. Divide both sides by 2, so natural log x equals 1. Now that I have the log by itself, I'm going to put this in exponential form. Natural log means base e, so this turns into e to the 1 equals x. So x equals e to the 1. Oh, and that's my answer. X has to equal e. Now, when we're solving equations with logarithms, in addition to solving, we actually have to check our solutions. And really, all we have to check is we have to make sure that the solutions we get satisfy the domain of the logarithmic functions that we're working with. In other words, we can't take the log of 0, and we can't take the log of negative numbers. So if the solutions we get give us zeros or negatives inside the logs, then they don't work. They aren't actually solutions. In this case, x equal e is a positive number that we're putting into the log, so this solution is fine. Let's take a look at another example. Solve the equation log base 2 of x plus log base 2 of x minus 2 equals 3. The first step is to isolate the log. We want one log by itself on one side of the equation. This time, to isolate the log, since we have a sum of logs, we can use that property and rewrite this as a log of a product. So log base 2 of x plus log base 2 of x minus 2 turns into log base 2 of x times x minus 2. That equals 3. Now that I have a single log on one side of the equation, I'm going to rewrite this in exponential form. We could also distribute the x, so x times x minus 2 becomes x squared minus 2x. In exponential form, the base is 2, so 2 to the 3 equals x squared minus 2x. 2 to the 3 is 8. And this is a quadratic equation. 8 equals x squared minus 2x. To solve, I'm going to set one side to 0, so minus the 8. And then we could factor or use the quadratic formula. This one we can factor because 4 times 2 is 8. If we make it a minus 4 and a plus 2, we get x equal 4 and x equal negative 2. Finally, we do have to check our solutions. Are both of these solutions in the domain of our logarithmic functions? If I plug 4 in, I get log base 2 of 4 plus log base 2 of 4 minus 2. 4 minus 2 is 2, and the important thing is we have positive numbers inside both of the logs. However, if I plug in the negative 2, I end up getting negatives inside my logs. We can't take the log of a negative, so my only solution is x equal 4. Now, if we have an equation that has a log with the same base on both sides, we can actually use the one-to-one property of logarithms. If we have the exact same base on both sides, then the thing inside the logs has to be equal. So to solve the equation, natural log of x squared equals natural log of 2x plus 3, the x squared has to equal the 2x plus 3. If I set one side to 0, I've got x squared minus 2x minus 3 equals 0. Factor, 3 times 1 is 3. If it's a minus 3 and a plus 1, that adds up to negative 2. So I have two possible solutions, x equal 3 and x equal negative 1. If I plug 3 in, log of 3 squared, log of 2 times 3 plus 3, both of those are positive numbers. That's all that matters. Same is true if we plug in the negative 1. Negative 1 squared is 1. 2 times negative 1 plus 3 is also 1. The important thing is that's a positive number, and so both of these solutions work or check out. Here's another one. Solve log of x minus 2 minus log of x equals log of 54. So I want a single log on each side, and so this time I have a difference of two logs. We can write that as a log of a quotient. So this equation can also be written as natural log of x minus 2 over x equals natural log of 54. Because we have a natural log on both sides, we can use that one-to-one property. The thing inside the logs must be equal. X minus 2 divided by x has to equal 54. To solve this equation, I'm going to multiply both sides by x. That gives me x minus 2 equals 54x. Subtract x from both sides, so negative 2 equals 53x. Divide both sides by 53. X equals negative 2 divided by 53. I have to check that solution. If I plug that in, I get a negative number. Minus 2 over 53 minus 2, that's definitely a negative number. Can't take the log of a negative, so this solution doesn't work. There are no other solutions. That means this equation has no solution. All right, that was my last example. As always, let me know if you have any questions from this video.